Okay, so I think we can get started. So today we have come on, I'm starting. Yo, did I start?
Sure.
Okay. Jesus. Okay. So our NCAR weekly seminar, and today's to be a little bit different. We're going to have it on Google Meet. Those of you watching remotely, please raise your hand, and we'll get you questions live here. And we're hoping a little bit more interactive. That's the reason we're doing it this way. Our speaker is John Dennis. He's a scientist in CISL, has a PhD in computer science. John co-leads a research group that focuses on improving the ability of large-scale geoscience applications to utilize current and future computing platforms. His research interests include parallel algorithm and compiler optimization, graph partitioning, I don't know what that is, and data-intensive computing. And today's talk, leveraging exascale technology to advance NCAR science within MMM. Please, those of you remotely, mute yourselves, and then we'll take questions even through the talk. John?
All right, thank you. This was the first of 7 talks, each of them targeting a particular laboratory. So you might see them frequently, and so they'll be identical in the first part and then specialized for each lab in the second part. So the exascale Tiger team was formed a while ago, and the goal was to determine the best course of action with respect to the utilization of exascale technology. So this kind of differs from exascale computing in the sense of we don't have an exascale budget to put an exascale computer on the floor. However, the institutions that do, like the DOE, use a particular kind of technology to use this. And so we wanted to see what this exascale technology can use to advance NCAR science objectives. And so we define exascale technology in these 4 categories: GPU enablement, lossy data compression, parallelization of workflow, post-processing, and cloud computing. And so we formed this NCAR-wide committee and to talk about kind of how best to press forward with this. And there's the name of my contributors, and this is the work of everybody. I'm just up here, the one who's up here talking. So, what we did is we created recommendations based upon 2 sources of information. A while ago, we sent out an NCAR-wide survey. It was targeted at how do you do computing? What are your limitations? What are your pain points? And then it was also based upon a second source of information. And I found this really fun, actually. So what we did is we went around to each of the laboratories and we asked scientists, what scientists would you perform if you could magically eliminate limitations? And so this was cool because you got the scientists talking about what they're excited about and trying to get them to kind of think outside the box. We didn't want them to say, well, CISL's never going to give me that allocation, and so I can't think about that. But we wanted them to, where would you go if you didn't have to worry about limitations? And so based upon those 2 sets of information, we came up with an overall recommendation for the NCAR Directorate, and then 7 laboratory-specific recommendations. And so we view this as a starting point for further discussion, and this was, obviously the first discussion that we're going to have. So the overall findings of the ETT committee, and this was kind of general for NCAR, is that NCAR staff aren't broadly practicing exascale software development. And they frequently cited the lack of prioritization from leadership. Funding, which is a problem for everybody, no matter what they're doing. Staff skills and familiarity with new technology. And really a time to shift to new paradigms while still accomplishing their existing workload. We heard these things over and over, and also meaningful cooperation or collaboration between scientists and software engineers with respect to kind of modern HPC and practices. Some of the other findings was that we saw tons of novel science outcomes or discoveries that could be enabled through the use of this this capability. I mean, we found them in every laboratory over and over. M-cubed, and so I'm going to talk about what we found in M-cubed. But anyway, it was just kind of, it was eye-opening that these technologies could benefit all of NCAR. There was also some limitations in okay, so this is overall, right? Prioritization of funding and staffing needs must be kind of baked into both the NCAR and LCPO strategies. They just can't come from the top and say this is important without providing funding for this. And we also thought that larger cross-lab software development activities were a potential kind of opportunity for working on culture change. We talked a lot about culture change in this committee. So these were the specific recommendations. We thought that the strategic plan should explicitly include the response to exascale technology, and say this is what the LCPO, for example, is going to do about this. We're not saying you have to do these 5 things. You just have to commit to and say you're going to do something, right? Another really critical one, and this is foster a co-design culture where science objectives represent a collaboration between scientific and software engineering leaderships. We kind of, in some laboratories, that's stronger than others. But it was, one of the things that I noticed the day before yesterday. Yaga Richter gave a great talk at the Day of Scientific Discovery. She talked about all the science objectives that this committee came up with, but then it was like, it seemed like there was a bunch of scientists that were creating this. Where were the software engineers? Well, they were in another committee, and they're learning about that information when it was presented. And so, it seems this seems problematic because you need the ability to the scientists to say, here's the 5 things I'm excited about. And then the software engineers will say, okay, one of these is really easy. We can do that in 6 months. The other one's going to take 20 FTE years to do it. So there needs to be kind of feedback into that process. I don't think that it's happening in some places in NCAR, not consistently. We wanted to identify internal and external funding to advance specific responses to ETT recommendations. They needed to come up with money to basically put these into action. They can't just do it as like the thing you're doing once you finish the rest of your work that you're over committed to doing. Communicate to staff the importance of exascale technology on the scientific mission of NCAR. When you get access to these slides, there'll be a complete list of recommendations, but these are kind of the key recommendations. Yep.
Could I comment? I'm on the same committee as Yana.
Yeah.
And we were maybe just
Judith? Judith?
Oh, you need to. Sorry, I thought.
I didn't design the room.
I forgot. Mason, let me just speak.
Good point. When are we going to get something like that?
just very quick, we were explicitly told not to do this because this will happen at a later stage. And so this is exactly the point you make, because we started with this and then we were told, no, don't look at feasibility, don't look at what you need, start with the science questions, but this is the point you make.
Yeah, but you kind of iterate on it.
I think
Right.
that's the plan.
Yes, yeah. So, okay, thanks.
Another one?
Any other comments on that?
Okay. It's interactive.
Okay, yes, no, this is exactly what I want, is interaction here. All right, so specifics to your laboratory. All right, so you're in actually a really good place because your science is really exascale friendly. It seems like a lot of the stuff you do, this was, you know, just a great fit for the technology itself. There's other laboratories that what they do is not as great of a fit, or it's kind of it fits well with part of their portfolio, but not with another part of the portfolio. So you're lucky here. It's also well positioned to leverage existing or exascale technology. This is because there's been multiple investments that have already been made, for example, in GPU enablement. The MPAS-A work, this was supported through, I'm probably missing people here, but Earthworks project, Weather Company, ASD project, the CM1 effort that was recently an ASD project, and the NCAR-LES. This is a prototype code that Ned has been working on with Ned Patton. Okay. Yes.
Please unmute yourself.
It wasn't a question.
No, it wasn't a question. Never mind. Sorry. I'm sorry.
David wants to be let in.
Is he in? This is my first Google Meet management thing.
So, however, I think we thought that basically the impact on the broader M-Cube community can be improved, and there's some specific. I'll comment on that in a bit. Okay, so we kind of we talked to the scientists, we listened to them, and we kind of determined these exascale friendly science objectives, and so these are science objectives that can benefit from exascale. This may or may not align with your strategic or institutional science objectives. These are kind of these are objectives that align with the technology roadmaps. And we broke them into the three categories. One of them is interesting and the other two are less interesting. Sorry. So there's modest, which can be achieved today or with a larger allocation. You didn't get the allocation you needed, so you can do it next year. There was I'm going to come back to the interesting. Unlikely. There was some that was mentioned that was not going to happen in 20 plus years. And this was just based upon the kind of the technology timeframes. And that was, sorry. But the interesting, I think, were that, so not currently possible or really challenging, but possibly in the next 3 to 10 years, you can, with a modest to significant amount of effort. And this is stuff that we classified as being interesting because it could be stuff that we could enable through a concerted kind of effort. And so the two things that came up there were there was mentioned 1 to 3 kilometers global simulations with ensembles, and as a exascale friendly science objective. This is possible, but it's kind of heroish runs. You don't know if you can really get ensembles. This is really challenging and painful, and so it's all, then we're talking about exascale technology that you might need to engage to be able to do this. So GPU enablement, lossy data compression, parallel post-processing. I don't think cloud computing actually gets you anything in this area. There was also more of a stretch, perhaps, was LES at a continental scale. That would be probably on the further out time frame. So those were a couple of science objectives that could be advanced or enabled. So some of the specific challenges for M cubed, and this was, so these were challenges that, you know, we kind of put everything on here that we thought was holding it back. And so some of these are simple and some of these are like really challenging, and we decided to put them all on there. So the number one was decentralized development of warp physics packages. And so I know this is a project that's underway, but I think we think this is really critical because there's no centralized repository for these package developments. So now multiple versions exist, and then you have multiple host models of flavors of them: MPAS-A, WRF, CM1, and on multiple compute platforms. You know, we ran into this when we wanted a particular microphysics package. There was a version in version 6 of MPAS-A that was GPUized. There's a version in 7 that was different. There was a version in CM1 that was not GPUized, and it had a different thermodynamic treatment. And then then we learned that NVIDIA had created one version, and they were willing to give it to us, but then it was like different than everything else. So it's kind of like, you know, you can't be doing the same work over and over. This is not unique to M cubed. I was involved with another microphysics package. It was ported to GPU 7 times. Now, the first couple of times we didn't know what we were doing, but the latter number were just because of kind of like in the wrong repository and everything like that. So you can't put that burden of 7 times repeat and get anywhere. So this is a critical piece. There was the other thing we found in this survey was that 2/3 of the survey respondents from M cubed were not familiar at all with GPU programming. So that's kind of a skill deficit issue. 61% were moderate to severely limited by disk space. There was also data analysis of large data volumes is difficult, which we heard consistently. And this was a lack of documentation regarding GPU enablement of MPAS-A. So, you know, the last one, maybe you tell somebody to do this and it's done in a couple months. These other ones are quite a bit more challenging. So, and then so some recommendations, and you know, again, we want to, you know, I want this to be a conversation, and this is a starting point. So, create a centralized repository for world physics package development. I think that's underway, and it's already being done. Add version numbers for the individual physics packages. You know, we need to know that a particular microphysics is version 7, right? And so then you can know that CM1 and WRF and use version 7. And then we're suggesting to shift the culture from a port 2 to develop on for physics packages. So what this means is that, you know, having the scientists develop the physics package, hand it off to a software engineer that then ports the package, and then they validate it. This is an endless cycle because the scientist is probably not going to stop innovating. And so you're just going to continue to repeat this, or you're going to have versions that are skewed out. You don't have you have the old version is on the GPU, and you have the two newer versions on the CPU, and so you need to kind of have it developed on the hardware. And so that, you know, I think there's some processes that you can put in place, some software processes like continuous integration, that you should be able to make this develop on easier. So the challenge of limited experience, provide training materials for all members of M-Cubed involved in scientific software development. I don't know if that sounds unpalatable or not. And then standardized testing and integration processes. So it should be easy to, move your common package from the different host models. Limitation of disk storage space. So we have a great solution to this, is called lossy data compression. It is, you have to validate it though for your particular science objectives. Some science objectives, it's going to work fine. Some, it's not. And so, but there's really two critical things here. You need to evaluate the science impact. That's probably done by scientists. And then but you need to also implement data compression within the package itself. And that's probably done by software engineers. You don't want to conflate those because we've seen other people conflate it and you just kind of get bottlenecked on it. Because if it's not in there, then then the scientists whose science objectives are tolerant of the lossy data compression can't move forward and can't use it. Data analysis, yeah.
Wait till later or just incorporate? So people know what you're talking about. Could you explain a little bit what you mean about like the scientific impact of lossy compression? Is it you can no longer calculate higher order fields from the data or derived fields, or what is the problem with having like a lower? I think of lossy as like kind of analogous to like a lower precision, like
Yes,
real star 2 instead of real star 4 or something.
That's correct. You lose information, and so if you're trying to close for example, if you're trying to close energy budgets, I don't know if you do that, but ocean modelers are trying to close energy budgets, and if they lose any of the precision, then they don't close their energy budgets, and it doesn't look good. If you think about maybe the impacts community who's trying to design a dam for kind of the water precipitation patterns, they know that there's uncertainty in these values, and they may only need a couple digits of accuracy, and they can throw the rest of it away. So it really kind of depends upon what you're trying to do and what you're trying to calculate.
Yeah. So for the training on like GPU programming, I would love to hear your comments on there's a lot of discussion about, I do think that in general, okay, so most scientists are able to be basic coders, and then you can move up into needing to provide code for scientific software, and then we have another level of maybe actually developing the scientific software itself, and then there's actually where you're looking at the basic dynamic and physics packages, but then there's also like being able to write code that runs on multiple hardwares. And we've been talking about like thinking about NCAR developing having a facility instead of just like hardware, of like actual community software facility. And part of that discussion is talking about abstractions, meaning like, does every scientific software developer actually need to know how to do all of the things? And I mean, like how, for example, be able to write code that runs on multiple different kinds of GPU architectures or different compilers, or and I think it becomes a more important question when we think about all of, NCAR's niche is that we're co-developing software of the community.
Yes.
And do we need all of our community members to then get training on GPU programming? I mean, I feel like there's another question here about like, how do we actually implement good code practices? I mean, we're just not gonna, I don't think it's realistic to think everybody's gonna be trained up on able to work with all kinds of hardware and all the compilers and all, you
Yeah.
know, so how, did you guys discuss that much?
We got into month-long arguments on that. So yes, we discussed a lot, and we didn't kind of come to a conclusion. We believe that it needs to be done. The clarity on how to do it is, and I'm sorry about that. There is some kind of George. I'll pick on George. George has been working with the CM1 code that's been GPUized, and he's been able to successfully modify it. He actually found a really subtle bug in the code that we could not find for a large amount of time. So I think this, to become an expert takes a long time. To become fluent enough to make contributions to the code that don't immediately break it is doable, I think. And I think you need to have, for example, there's the notion of continuous integration where you check the code before it's submitted to this repository. And so there should be checks that run it on the GPU, checks that run it on the CPU, and you kind of check that. And so you can automate some of this if you come up with a good processes. Because, you can't push this training to the entire community, right? But you can develop structures that make it easier. So, yeah. All right. Data analysis for large data volumes is challenging. There's the ESDS community. I'm blanking on the acronym, the meaning of it, John.
Persistent data science.
Okay, thank you. So they're talking about that, and it's a whole community that is addressing those challenges. And so lack of a documentation, this is just increase kind of modifying a priority of somebody's task list. So anyway, so those specific recommendations, I'm hoping that this is kind of a discussion, the start of a discussion. Any questions?
Hi, John.
Hi.
I've gone to a couple exascale meetings, and it seems like that's a fuzzy question. What is an exascale machine?
Yes.
And so one of the workshops I went to, they said, well, it could be an assortment of accelerators, et cetera, but with variable precision on each computing core. And I'm going, if you're going to run,
That's a scary feature.
that's not, I'm not going to do that.
Yeah.
And so the other comment was I was at Argonne and they mentioned the same kind of thing. And they said, well, exascale computing will just take longer to get, the time to solution will just be longer because you'll just run it bigger and it'll just take longer to get there. So I guess, what do you envision as an exascale machine?
Well, I want to get it back to it's the technology, right? Because you're I don't know if I'm sure people in this room are going to have access to an exascale machine, but everybody's going to have access to the exascale technology. So it's going to be something GPU-like. You're going to have to reduce your data volumes because you can't store it on disk. So it's going to use this technology, right? So my definition, you've turned a compute problem into an IO problem. But that's my definition of a supercomputer.
So I think others are in the same situation as we are, isn't it? How much do we look at other institutions like DOE, for example, or I know for NOAA or several like Max Planck in Germany, they face the same challenges and have similar goals than we have.
Yeah.
Um,
They're putting a lot.
Should we coordinate or should we look what they do? And do you think there will be, like, for example, on the analysis side, it seems like Python won out over all other solutions.
Mhm.
Do you think something will happen along these lines where some path will be the most prominent in the future for going to exascale with our software?
Well, that's a challenge. Is what we're trying to plan for technology that we don't quite understand. One of the key things that you see in the difference in the DOE and the European efforts is they're actually putting a lot of money into the software development. I'm not seeing that in this institution, right? And so they're and they've come up with a variety of ideas. I've been watching them and for a number of years. But I mean, everybody's dealing with this because it's how do you use the computer that you're going to get in the future? So.
But is everybody dealing with it differently? It feels like that a little bit.
There is variations. I mean, the Europeans are pretty big on domain-specific languages, and the DOE likes C++ productivity languages. You have to balance that between our workforce. What is our workforce willing to absorb or can absorb? So.
Just a quick comment. You might want to read.
Oh, where do I see that?
Bottom right.
Oh, do I? Okay. Okay. So what's science physics needs exascale simulations and the related question. Wait, are necessary.
Yeah, John, this was kind of in response to the previous question about what's an exascale machine, right? At present, exascale machines are.
Ben, we couldn't hear you. Is it possible to turn the volume up in here? Okay, he's trying. Ben, could you say that again?
Yeah, sorry, that was just posted in. Are you hearing me okay?
Yes, thank you.
Yeah, that was just in response to the previous question about what's an exascale machine, right? Like the real question is what physics and science need exascale simulation capability back to the drivers. And right now, the hardware is the best collection of resources that can satisfy that at the moment.
Yeah, I mean, the science objectives are the ability to do the ability to do 1 to 3 kilometer global simulations with ensembles, right, and with increasingly long timescales, or LES at continental scale. So.
Okay, that leads nicely into the question I was about to ask, so I'll go ahead and ask it. So a lot of people are probably wondering how far away we are from that now, because we just got a new computer. It's called Derecho. A lot of our staff haven't even tried that yet.
Yeah.
Haven't moved over yet. So how far are we from exascale now? Are we like an order of magnitude away or 2 orders of magnitude away?
Maybe 3.
Maybe 3 orders of magnitude. So the kind of problems we're running now in M-Cube, you say, are like 1,000 times smaller than what you're talking about?
At least. Yeah.
So
I mean, you need to think big, right? And I'll pick on Bill here because Bill was thinking really big, right? When you're describing kind of like what 1 meter across the globe, right? This is an exascale problem that you're probably never going to get to.
With ensembles.
Yeah, that's correct. With ensembles
And chemistry.
and correct, and chemistry. So.
Okay, thanks. I had one other quick question. You mentioned training or learning how to use GPUs, but as someone that knows just a little bit about that, I know there's many different ways to use GPUs. So I'm wondering, where do you think the tools are going? Do you think we've kind of settled on the tools that we're probably going to be using? I'm thinking mostly for like running the jobs. Like we put OpenACC directive. You and Sherry primarily put OpenACC directives into CM1.
Yeah.
Because it's what you could do at the time. It was available. A couple of years later, you think maybe, oh, we should have done something else, or we should have waited for, ISO Fortran to have that capability, or should we all be learning CUDA, or what? Could you just comment on this a little bit? Because I think saying that, we should be training on GPUs is, to me, it doesn't open up like how vast of a learning knowledge base that could be. So I was hoping you could elaborate a little bit.
Okay, this is actually great, and because I'm looking at that over there. So we started with OpenACC, and we did all of CM1, and we replaced tons of directives, and there was thousands of them, and so with this NCAR-LES code, Ned produced kind of like this simplified operators. And ISO Fortran came out, and so we tried it. And lo and behold, it works quite well. You can write it, and it looks like regular Fortran, and it just converts it into directives based. And so it's not a silver bullet, but it's cleaner. And so kind of ISO languages. It doesn't solve all the problems. You still have to do data movement, so you can't eliminate all the directives. So if I was doing CM1 over, I would put ISO Fortran in it, which is what we're targeting for the LES code. Yeah, so it's 50 derechos provides an exaflop. So if yeah.
Something about this role.
I waited for it. I'm going to comment too. I think it's a good question that Andreas brought up. Is it the same that we're trying to solve as, let's say, an operational center who does not have to have the community in the mind, but can really optimize for their application in their architecture? That's just sort of a comment. My question was really, in your opinion, is it really that we'll have to move to GPUs because this is the only processing unit that will be available in the future? I know some other countries are heavily investing into CPUs. So is it that we basically, are we beyond the time where we're having the GPU conversation and it's really going to be the next models, or are there other processors out? And in particular, for a while, there was a lot of talk about in-exec computing. I haven't heard anything about this.
Yeah.
So there's CPUs that have a known or not known error characteristics, depending on how it's being developed. So those were my two questions. My third one is I've been heavily involved in ESDS. We were taught with Python, if you have Dask, you don't need to parallelize. It does everything under the hood. You just need to write the code. And that obviously is not the case, not in my experience, if you go to really large data sets.
Yeah.
And so sometimes it sounds like something does the work for you, and you still end up having to do quite a bit of data shoveling underneath and expertise.
I think I want you to ask the questions again, because I'm going to answer the first one. Okay, so there's a big difference in the amount of electricity that it takes to run simulations depending upon your choice of platform. So GPUs you use considerably less electricity. And so it's going to be a practical perspective of that. Do they want to pay the electricity bill to enable you to do your science? right? And so that's what it's kind of pushing it into this energy efficiency. And so we can't. It's unfortunate, George. We were wanting to kind of measure the difference in electricity usage based upon CM1. We can't measure that today because there's something going on with the system, but it's significant. So, and the other thing to appreciate is that the people that do have exascale budgets, and I'm going to call that the DOE, they may disagree. They are buying systems that are configured in such a way that they can afford the money, and and so we have to kind of use their hardware. So that's what's pushing it towards. You'll still continue to have CPUs for probably a while. It's just a question of how expensive they will be to run, how expensive they will be to buy.
Inexact computing.
Oh, I don't know about inexact computing. That seems kind of scary. I mean, where I've run into this is, do you need full precision everywhere? And so I think the answer is probably no, but figuring out how to do it properly it would be very challenging. And again, that would be an example of, so for example, in the GPUs, you can get more flops if you drop the precision down. And so in some pieces of code, that's perfectly fine, and others it's not going to cut it. So it's a partial solution, I think.
It was, do we have to do the same? The third one was a common. Sometimes something looks parallel with task, and you still need to do a lot of work. Now, but I think you answered this question of, if you try to have a community model, is there other constraints than if you're developing, let's say, an operational system?
Yeah, exactly.
Yeah, I'm particularly interested in the lossy data compression and stuff,
Okay.
which I think is going to be, one of the big bottlenecks for a lot of our problems going forward. It seemed, and maybe I misunderstood this, you were kind of advocating for inline, doing that inline in some of these models. I was wondering what kind of feasibility in doing that at the post-processing stage would be, like sort of the trade-offs. Or is there a specific path that you're envisioning here for the lossy compression?
Well, okay, so right now you can certainly output it and then do it as a post-processing step. The problem is then you hit the disk once with the full resolution data, and then you hit the disk again with a lower with a reduced precision data. So that's accessing a disk, and then you might get nervous and say, I better keep the full precision data around in case I realize that something was really lost in that. And so that gets into kind of workflow issues and complexity of the workflow. So ideally, you would want to not even create it at the full precision.
Yeah, that makes sense. I guess one issue is whether it's going to be kind of a runtime storage issue that's the problem, or more long-term storage. That's a problem.
I think the long-term storage is an issue, is a critical issue, and yeah, and
so I have a question about training, because I was on the team, so I should know this. But it seems like, at least implicitly, a lot of the recommendations are about more training of the workforce, which in general seems good. But we're already complaining about the workload, so it's essentially you have to take something away before you can put something new on there. Because if you talk about training now, that would just be you're adding more stuff to our workload. Yeah, I have no idea about GPUs, so if I were to be training it would probably take a lot of time. So I'm wondering if, with large language models, do you see a way of that we're just pasting our code into ChatGPT and say, can you GPUize it? Is that possible that something like that will work in the future, rather than us becoming experts, or at least quasi-experts in it? Because not everyone is going to be like George Bryan. You know, that he's always highlighted as the poster child, but you know, CM1 is his model. So he knows it in and out. You know, I'm dealing with GPU MPAS, which is actually in a state of near unusability, and yeah.
I
respond first.
yes, go ahead, go for it.
Yeah, just with regards to training, I don't think everyone needs to be an expert. Training could be as simple as learning to speak the language that software engineers speak, or learning some of the technical details, not all of them, some of them, so that you can interact in a more, you know, on a level, not even level playing ground, like on the same plane of existence, or learn to meet someone halfway. So I think the training is more about, you know, teaching some of the basics so that you can understand and interact with, rather than doing it yourself. That's kind of how I see it. Maybe, John, do you see it differently?
No, I don't. That's a good description. It's it does take.
It's an investment, yeah.
But I mean, it's, you know, you could say that, you know, in the past, maybe people would write equations on papers and hand them to somebody to do, right? So you already have a certain high degree of training. It's the fact that you actually write your own code and compile it, and right. But no, I agree. It's challenging. What do you cut out, or what do you push aside?
I have, I think, a question that's related to use question with the data output. I think we're not only developing community models, we also produce community data sets.
Yes.
Did you think about how to serve these data sets to the community once we reach exascale? Like, the data volume will be massive, and like downloading the data and analyzing it on local machines will probably become infeasible.
That's, yeah.
So is there a solution that you?
Well, I mean, I think data compression is the only solution that I see. Do you want to, maybe you're the.
Yeah, so there's a lot there, but I think, you know, definitely echo what John said. I think lossy data compression plays a role here in dealing with the data volumes, but also moving away from the download model. And there's a lot going on in that space to allow analysis to happen in a data proximate way, close to the source of the data, or when you are having to move the data, not downloading the data set in its entirety, but only accessing those subsets of the data that you need for your analyses and pulling them directly into your analysis process.
I don't want to dominate the discussion, but I did have a thought. I think the issue is one of data reduction, is how you should frame this, not of necessarily data compression. So for example, what you have up on the screen here, I've thought a bit about this, LES at continental scale. If someone decided they wanted to do this, I don't think we would be arguing. We want to write out our output files in the native resolution. We'd probably down filter it to, like, I don't know, 5 kilometers. You'd even have like a, you know, coarser resolution analogs, because the idea of going to LES at continental scale is that, here's the ultimate thought here, is that PBL parameterization is impossible, is the premise. So therefore, you go to high resolution where you can resolve the IDs, but you don't necessarily want to write all that information out. So you got to down filter, and that would involve processing itself. And you also want to put diagnostics in your code. If we were to do that, we would want to do things like add in calculations of gust factor that would be inlined into the code, and you just write out that gust factor out at, I don't know, kilometer or 10 kilometer scale. And you just got to think differently. You have to calculate things more during the model run. I mean, a lot of LES people do this already, and we know about it. It seems like the weather prediction community doesn't do this as much. But going back to my main point, yeah, data reduction for further analysis and storage is how I would present the problem. That's kind of more for you in the Tiger team, I guess.
Preemptive analysis, meaning analysis during the run, predisposing what you want to look at, or thinking you know what you want to look at, and only saving the essential volumes to go back and restart if you need, if you mess something up or whatever. I mean, there's just another way to think of it where you don't necessarily store all the data, you store part of the data or enough of the data at one instance to then go back and restart. And because if the computation is so cheap these days, or will be,
Yeah,
then you just don't store as much.
I mean, there's already a huge amount of data reduction that's going on. So, you know, in climate models, they'll capture the averages over the month. You're not outputting every time step information. So that's already a huge kind of information loss. And because you decide that you don't need all that information. You know, there's also a choice of, you know, do you do 4 bytes or 8 byte reals output? Well, you don't probably. You do 4 bytes output because you don't need the extra. So there's already information loss and, you know, and data reduction that's going on. I think you need to continue to push on that.
Okay, I don't know if the audience has exhausted itself yet. I'm exhausted. All right, there's opportunities for further interrogation of our speaker out here by the cookies and coffee. Thanks again.
Yep, thank you.